This thing of looking at the state here, comparing to state there, any place on the lattice, that's an operation. I tell you what you do. But derivative turns out to be a linear operator, and it's actually very easily defined as a matrix. Let me define something called upper shift matrix. So this operator is conveniently done in terms of Kronecker delta functions. So let's define a matrix object with two indices, which has 0 enters every place except unless the first index is neighboring the second index by unit length in direction mu, but now we have one dimension, so we can drop that index. And what is this thing? So it's easier to understand it if we write it as a matrix. So it's a thing that is 0 on diagonal because the two indices have to differ by 1. And it's off by 1 unit. So that means that when the difference is exactly 1, we get 1. And the rest is 0. And in particular, this lower left corner is 0. You'll see in a second why I care about lower left corner. So as a matrix, we understand what it does. It takes a vector and when you multiply it, what used to be first component is now replaced by the second component, etc. But let's think what it does as a matrix. If you square it, then it shifts components by 2, which means it looks like that. And now, if you repeat this L times, if this is L by L matrix, what happens is that after L steps, all the ones march off to the upper right corner and then they disappear. So this representation is nilpotent. I think it's one of those weird matrices that if you apply it a few times, you get a 0. So it dies on you. And the reason why this is happening is that this is not a nice set of boundary conditions that you have chosen. Because, as I'll try to argue now, what you really want to do is you want to choose periodic boundary conditions. Now, this will just seem like a choice, but I think it's more fundamental than that. I'll try to explain. And what that means is you write this matrix just like we did above. 0, 1, 0, 1, 0, 1. But then when you get to the lower corner, you're about to lose this 1, but you stick it in here and make everybody else 0. What's good about that? As you shift the matrix, you'll find out that this 1 will also shift. And these things that disappeared as I apply the matrix, they'll reappear in lower left corner and they'll propagate as a diagonal. And when you do this L times, you'll actually get to identity. So it's not sufficient just to write that when you take a derivative, you have to compare the two neighboring points. That's what this shift matrix written into the canonical data does. But you also have to make sure that when you come to what seems to be edge, but edge is totally arbitrary. You know, you had an infinite line with infinitely many integer points on it. You took a part of it to represent the thing. And when you come to the edge, you have to take this point, the next one. If you make them periodic, you make a seamless representation of the infinite line by a circle. And that's good news. Why the physicists love periodic boundary conditions. Well, we love them because we want all points on the world that we work on to be democratically equal. You don't want to have somebody in the center and then less important points away from it, because that would introduce an artificial imbalance in something that in original problem had no distinction. No matter what point I take, if I have a periodic boundary condition, then I'm always size of, if my number of points is L, capital L, I'm always halfway from the edge. Because with periodic boundary condition, there is no boundary. Everybody is equally good. Now, that reflects something much deeper, which is a central theme of much of what we'll do in the remainder of this course. We want to formulate our theories as being translationally invariant. Now, on the line, this is pretty obvious what it means. I have an infinite line going from plus or minus infinity. And what I decide to put origin and start measuring my distance from is my choice. It doesn't really matter. No law of nature should care about it. So infinite line is naturally homogeneous. All parts of it are equal. And when we make something finite, because on a computer, not only cannot we put infinitely many continuous points, but we cannot also take infinitely many discrete points from a line. It has to be a finite number. We want to preserve translational invariance. Translational invariance on a bounded domain. Now, let me redraw our problem in a way that makes it very clear what is translational invariance is. Instead of drawing an infinite line, I'll draw a circle. I will discretize it into L being an integer, hopefully a large integer, L points. So my coordinate, which used to be a continuous length measured on a circle, is now L points. And then my field measured on this circle has value 0 at what I call 0.12 to the last point, which in this case is called L minus 1 because L and 0 are the same. So periodic boundary means that f of L equals f of 0. But not only that, if I move it by j points, they also agree because I'm just on a circle. So once I've gone around all times, everything repeats. Now we can think of this as a vector. So when I say a lattice state, I really mean this vector, which is the values of the field on all the points. And I can draw it as a circle, which is a necklace with all points around it. And now I have to understand what does shift operator that I just defined do. Well, shift operator will be a cyclic permutation of lattice states. I'll have the same lattice state, but I will relabel its position because I've changed my coordinate system in a cyclic manner. So it's a cyclic permutation of lattice state. So it's very important to understand that we are always having coordinate and states, and what this does is it doesn't change the state physically, but it changes it in your coordinates because you've changed it. So on every point, you have a new value of the field. In other words, when you apply the shift operator to your state, what happens is it moves. Remember how it worked? It had ones off just above the diagonal, which means when you multiply it by a vector, the second component is promoted to the first component. So now this becomes phi of 1, phi of 2, And the last guy, because we stuck this thing in a corner here, the last guy is now phi 0. So you haven't lost anything. The stupid boundary condition you started first was just chopping off the state until nothing was left. That's not very useful. And if I draw this in my coordinate system, it means I have to draw the circle. Circle has coordinate 0, minus L minus 1, 1, 2, 3, which are my coordinates, discrete coordinates. But now what lives on the first state is phi of 1, not phi of 0. What lives on the second state, lattice side, is phi of 2, phi of 3, and so on. And this guy is actually phi of 0. So you can see these two states are not very different. You just turn them by a little notch. And then you can check this transposition we did before, which went in negative direction, is also the inverse of the operation because, we can notch it one way this way and then back by 1. That's the inverse. And the action of that operation is that it takes something that used to be F1 and puts it here. In first place, it put what it used to be to the left, F1 minus 1. So it's a cyclic permutation in the opposite direction. But main thing about symmetry operations is they relabel stuff, but they do not destroy anything. What that's the thing a nilpotent operator would do. They just put F0 here, F1 here, F2 here, phi 2 here, phi 3 here. In other words, just move it in the other way. So this is a nice cyclic operation, which in infinite alignment, I just change origin of my coordinates, but here it means I change it on a circle on a finite set without messing with the state itself. I just have relabeled its vector coordinate.